Hi, in the previous video, you have learned briefly about set theory. In this video, we will be looking at events. In particular, often in scientific study, we conduct experiments to collect data. Outcomes of each experiment can be studied using set theory, and the chances of an outcome happening can be understood via probability. More formally, an experiment is the process by which an observation is made. An experiment can be deterministic or random depending on the way we conduct the experiments. For instance, if your experiment is to observe the direction where sun is rising, it's a deterministic one. There is no uncertainty in it. We certainly know that sun is going to rise in the east. On the other hand, if you're tossing a coin, let's consider a fair coin toss where either head shows up or tail shows up. Until you see what showed up, we are not certain about exactly what is the outcome. Such an experiment is called a random experiment. Set of possible outcomes of an experiment is called an event. In the above example, an event could be head showing up or it could be tail showing up. Collect all these outcomes, then you create sample space and it's denoted as omega. So, to be precise, omega or the sample space is the set of all possible outcomes of an experiment. Now consider more complicated example where instead of one coin toss, we now have two coin tosses, which we are tossing simultaneously. And then each time we conduct this experiment, since there are two coins, either you have both heads or head and tail or tail and head or tail and tail. So if you collect all these possible options, then you create sample space which is omega. As you can see, this is a set which consists of all possible outcomes. Once we have it, we can define subsets of this sample space. Those things are called events. For example, A, let's take it, is the set consists of this particular outcome where first coin has a tail on it and the second coin has head on it. That is one event. Take event B where it consists of two possible outcomes. One is tail and head and tail and tail. So we say that event B occurs if one of these outcomes shows up. We understand how sets can be useful for representing events. Let's look at how events can be represented using Venn diagram, and we do that with the last example we consider. Clearly, we started using set theory to represent outcomes of random experiments. For this example, let's look at how the Venn diagram looks like. Now, omega becomes the universal set for this random experiment, and then we have four possible outcomes. This is one outcome where head and tail shows up. Then you have another outcome, this tail and tail, like that. You have other two outcomes. So in the above example, we defined A being a set consists of one particular outcome, that is tail on the first coin and head on the second coin. So A consists of, as you can see in this figure, A consists of only one point. On the other hand, we have set B, which consists of two outcomes. Uh, First coin showing tail and the second coin showing head, as well as for both the coins showing tails. So B becomes the set. B represents the event where both the outcomes are inside. Similarly, if you consider C, is a set where both the coins are showing the same result, then C is set consists of two elements, head and head, and tails and tails. So this is how we represent. Once we have, we can define this combination of these events, just like the way we define relationships on set. Suppose you consider two events, event A and B, then their union, which we saw as defined as follows, denotes the event that either A occurs or B occurs or both occur. Similarly, we can define intersection as well. For any two events A and B, their intersection, as you have seen in the previous video, denoted like this, represents the event that both the events A and B occur. The empty set, which is a null set we have defined, represents an impossible event. We say impossible because when you conduct an experiment, there will be some outcome. We expect that there is some outcome. So the chances of seeing empty set is zero. That's why we call them impossible set. And furthermore, we have this disjoint sets defined in the previous video. Similarly, for any events A and B, if they are disjoint, then the events A and B are called disjoint events or mutual exclusive events. And this is interpreted as both the events not occurring simultaneously. All right. If you think about a coin toss, either head occurs or tail occurs. You will never see both occurring simultaneously. So if A is an event of heads occurring and B is an event of tail occurring, they are mutually exclusive. Similarly, in the past we have seen complement of a set. Here, for any event A, its complement denotes the event that A does not occur. So in coin toss experiment, head doesn't occur is same as saying that tail occurs. So if A is heads occurring, then A complement is tails occurring. Finally, for any two events A and B, if A is subset of B, that is the case in this Venn diagram where A is a subset of B, then occurrence of A implies the occurrence of B. If you see, what is B here? The set B is essentially saying that I don't care what is the result on second coin toss. I want first coin toss to have tails on it. So if A occurs, which is tail occurring on the first coin and head occurring on the second coin, as you can see, then automatically B is satisfied. That's why A implies occurrence of the event B.